Hey there, I'm Red Dragon Web Design. Today we are going to do Hello World in assembly language. We're going to use the website CodeWars. Um, and I also want to talk about some data types and some constants because those are something we're going to need to know how to do Hello World. In the last video we did multiplication and basic variable assignment, register assignment, um, and all you didn't even need to log into CodeWars for that. But for this one, we're going to need to sign up for an account. Um, in my case, I already have an account, so I'm just going to log in. You can link into your GitHub, so you don't even need to create an account if you already have a GitHub. So we're going to log in real quick. And then just a quick overview on CodeWars. It has kind of a martial arts theme. So you start off at 8 Caillou, which is like a white belt. And it goes 8's the beginner level, and then it goes all the way to 1 Caillou, and they have like different belt colors and different levels. So that's really cool. That kind of keeps you motivated, gives you something to work on. And you can do CodeWars in multiple languages. Um, anyway, let's get to the exercise. We'll click on kata and we'll type in hello world. Hit enter. And let's see, which one did I do? This one has a check mark, so I think this is the one that I did. So do this function 1 hello world. 8 Caillou, it's a low level. Just getting started, just getting warmed up. So we'll click on NASM, assembly language. So right away we see some things I introduced in the last video. We see a section text, which is their code word for the code section. Anything below this is going to be code. And then don't forget there's also a section data that you can use, and you don't always need to use it, but we're going to need to use it for this problem. Anything that is a constant, pretty much, is going to be placed in this section. So I'll get to that in a second. Global greet, talked about that in the last video. You just need to global the name of your function in all of the CodeWars problems. A semicolon here is a comment. We can just delete that real quick. XOR a register with a register. This is something you'll see a lot in assembly language. It's a shortcut for saying RAX 0. As you'll recall, this is the same as RAX equals 0. So move RAX 0 means make RAX equal 0. But another way to write this, just for 0 only, is XOR RAX. And this is a shortcut that I believe they do it because it's a little bit quicker. I think this executes a little bit quicker than this move instruction for some reason. So anyway, this is just something you'll have to memorize. This shows up all the time. And then ret for return. Remember, this whole thing right here is a function. There's other assembly code wrapped around it that you can't see that makes this work. CodeWars just wants you to write the function. And return is how you're going to exit the function. And don't forget from the last video as well, the value we return is always RAX. Whatever's in RAX will be the return value for the entire function. Alright, so this one's pretty easy. So I think the best way to teach this one is I'm just going to type out the solution for you, and then I will spend the rest of the video explaining the solution and going a little bit more in depth into some of the things the solution requires knowing, such as data types. So first things first, let's figure out what we actually need to print or return from this function. Over here it says hello world in lowercase, but down here in the test cases it actually says hello world and it's capitalized. So I'm going to go with these. I think this test case is probably what they're looking for. So let's go ahead and use that. So what we're going to do to make a string constant, remember if you've studied C or a low-level programming language, you know that a string is just an array of chars, an array of characters. And an array, of course, is the same variable type over and over again a certain number of times. So, first thing we want to do is we want to create a name for this. We're going to label it. The same way our function here is named greet, we're actually going to name our data too. In this case, we'll just call it hello, colon. Bam. Okay, so now we have a label that we can jump to in our code. And that's also going to be the name of our string, kind of. And then after that, we need to declare what we are making an array of, what the data is going to be. And the way you do this in assembly language is you tell it how wide the data is in bytes. So a char is 1 byte. It's 8 bits, 1 byte, and it has a range of 0 to 255. So we're gonna do db data byte, and then after that we can just put our string. We can just enclose it in double quotes here, and then we can just type what we want in there, and it will take care of turning that into chars for us. So we're going to type hello world exclamation mark, and we're going to make sure to capitalize it, because that's what the test case wants. When you're doing CodeWars problems, you can always check out the test cases. They have 2 sets of tests. They have a set of tests that you can see, and you can even add your own tests down here. And then they have a set of tests that you can't see. Those are random tests, and that's to keep you from just figuring out what the tests are and then having your function return that data in order to cheat and pass the kata, pass the exercise. So anyway, we can see exactly what the string they want is. We put it up here. And then we're going to do one more thing. In C, you don't have to do this. It's not like this in every language, but in C and in what we're doing here, we always want to end our strings with an ASCII 0, a null character. That's how C language and this particular, I guess, dialect of assembly knows where the end of the string is. There's other ways to do this, but this is how we're going to do it. We're going to have hello world, and then the last character in this array of chars is going to be an ASCII 0. And the way you do that, like I could put 2 ASCII zeros here if I wanted. I could do 0, 0. I could put a different ASCII character, like whatever 40 is. I could do that just by adding commas and not putting quotes around it and typing a number. So anyway, we're going to do that. And then down here, we can get rid of all this. Got to figure out what we want to return from this function. We want to return a pointer to this hello world string. So how do we get a pointer to the hello world string? We're going to move into RAX. Remember, pointers are always going to be the widest register. They're always going to be that 64-bit register. So you want to use R. And the A register, RAX, is always going to be the return data. So whatever you put in there, and then whatever's sitting there when you do a return statement is what will return out of the function. And then we want to move into RAX a pointer to this data. Super simple. We'll just type hello. Because remember, our label here is named hello. So what that'll do is when this gets compiled, the compiler or assembler, or whatever you want to call it, will put this wherever it puts it, and then it will work on this, and then at the very end, after it figures out the memory addresses of all this different stuff, it will replace this hello with the memory address of that. It'll take care of that for you. So that's what we're doing here. We're telling the compiler how to compile this, where the pointer is that we need. And this will probably pass. Let's do a quick test. Bam. So the first time I did this, I actually got really stuck on this. All these little things I kind of talked about and guided you through right now, like it's kind of hard to figure those out on your own. You can get completely stuck if you don't know, a lot about, the widths of data types, or exactly what command you need to make a constant, and how wide the constant needs to be, and how to put that null character in there. So I want to talk a little bit more about that stuff in detail before we submit our solution here. Alright, let's quickly talk about data types so that we kind of understand the solution we typed here. We understand, what db means, what dd means, dw, the different things you can put here, and you kind of understand what's going on in assembly in general when we have ints and chars and eventually floats. So variable types. Assembly is very flexible. You could actually, in theory, you could kind of make up your own variable types. Like you could have an integer that's only 16 bits wide, and you could use assembly instructions on that and it would work just fine. But for the sake of just using a standard system, I am going to use everything that we use in the computer programming language C. C is one of the lowest level languages you can get to before assembly, and it's kind of a higher level assembly in some ways. It kind of automates some of the stuff that we do in assembly. So that's really a good language to borrow from. It kind of has all the best practices that evolved between when assembly was invented in I guess the 60s and 70s, and it kind of evolved into the C language was very popular for a while. It was one of the top languages back in like the 90s, I guess, 80s, 90s. Um, between it was like assembly, and then I think it was Fortran, and then Pascal, and then C, and then some languages after that. Anyway, it's a great language to learn a lot about how the computer works at a low level, while at the same time combining efficiencies and best practices. So anyway, some of the basic data types in C include a char, a character. It's 1 byte, which means it's 8 bits, 2 nibbles. Has a range of 0 to 255, and these correspond to the ASCII characters. Here's a quick overview of the ASCII characters. Let me zoom in a little bit here. The beginning here, you have these control characters. They're white space characters that you can't necessarily see, and a lot of them are completely obsolete. You never use them anymore, like these right here. From this list, you pretty much only use like line feed, carriage return. That's how you basically make an enter character or a new line. Null character to terminate strings. There's a horizontal tab in here somewhere. And then these middle ASCII characters, 32 through 126, these are kind of the standard keyboard characters. And then once you get a little bit higher, that is some control characters that were useful, or there's some diacritic characters from other languages. And then towards the end here, these are actually characters from the DOS days of computing. You would use these to build, you'd put borders around things. Instead of drawing a line, you would actually combine these characters to make it look like there's a border. But anyway, that gives you the basic idea. There's 0 through 255 is the basic ASCII 255, or ASCII 256. So those are your chars. And then you have signed ints and unsigned ints. The difference between a signed int and an unsigned int is that a signed int uses the top half of its range to represent negative numbers. And it does that through something called 2's complement, which I'll get to in a second. And then, of course, you can make arrays out of these things. You can make a char array, you can make an int array, you can make whatever you want for arrays. So quickly, here's a more detailed list of pretty much every variable type in C. The ones I didn't cover are the less common ones. Short is a type of shorter integer that's only 16 bits wide. Long is the same thing as int on most systems nowadays, on most 64-bit systems. A long is a 64-bit int that fills up the entire register. And then there's also floats and doubles. Floats and long doubles as well. Floats are how you represent decimal numbers. There's a way to do that. So here's how a float is represented in C and in assembly, the way we're going to use it. The first bit is a sign, positive or negative. The next 8 bits are an exponent power of 2, so that's 2 to the whatever. And then the mantissa is kind of the remainder of that, like how much you alter the 2 to the x, plus or minus, and including the decimal. This slide has a little better explanation of everything. So you have the sign, positive or negative here, and then you have the 2 to the n here. And then this is the mantissa again. It looks like they add 1 plus, and then the rest of that is actually a decimal value. And then they take all that and they plug it into this formula, and then that is how it's represented in decimal base 10. So for the example, this value would end up being negative 0.21875. But we don't need to go into too much detail right now. Just know that any float that you want to represent in C or in assembly is going to be converted into a 32-bit wide number, and the pieces of that number are going to be this sign, this exponent, and this mantissa. Another important thing to note is that the size of your variable type is going to determine the size of the register that you need to use. For example, if you're using a 1-byte char, you are going to want to use, for example, AL or AH to store it, probably AL. If you're using an int, you're going to want to use an E, a register that begins with E, or ends in, if it's like a R8, let's say it'd be R8D, ends in D. And then if you're representing, a long, you'd want to use RAX, etc., etc. And then there's actually special registers we haven't talked about yet for floating point. They use special registers and even special instructions, but we'll get to those a little bit later. Just to recap, here's another table to kind of show all the different data types and their widths and what registers you use. They also have special names. So, example, a 1-byte data type is called a byte, of course. 2 bytes is a word. 4 bytes would be a double word. 8 bytes would be a quad word. And then their special syntax we'll use a little bit later as we get into more advanced assembly. But the main thing that we want for this particular lesson, you get a nice little rectangle here, is this section. Hold on. Let's do an outline. No fill. Nice and thick. And we'll make it red. This section right here, NASM data. Because these are the commands we use to make our constant that said hello world that was filled with chars. db corresponds to byte, w to word, D to double, and Q to quad. Alright, back to 2's complement for a second. As you may remember, 2's complement is what we use to make a signed integer. Remember, a signed integer is an integer whose top half of the range is negative. So for example, if you had an integer that was just 0 to 8, or 0 to 7, I guess, let's call it that'd be like what, a 3-bit integer, for example. If it was range 0 to 7 and it was a signed integer, all of a sudden 0 to 3 is now just the regular positive, and that 4 to 7 is actually the negative numbers. 7 would be -1, 6 would be -2, 5 would be -3, etc. And 2's complement is a way to easily convert to that. The logic for it is really simple. So that means a computer can quickly compute it. If you want to convert an unsigned number to a signed number, 2's complemented basically, all you do is do a logical not, this little tilde character here. You do a logical not, and then you add 1. So for example, if you want to take the number 1 and you want to make it a -1 at the bit level, you start with 1. You negate it, which flips all the bits. You do this logical not. So 0, 0, 0, 0, 0, 0, 0, 1 flips to 1, 1, 1, 1, 1, 1, 1, 0, and then you simply add 1 to it. And then all of a sudden you have a -1. So what that did is it was at 0, and it actually went all the way to the end of that range. So whatever the width of that variable was, that is the last number that it's going to go to. So if this were a wider variable, this might be like ff, ff. Once it goes from 0 to -1, it goes all the way around. Let's continue. Let's turn 2 into -2. Same thing. We negate it. We flip these bits. We alternate them. We toggle them. And then we add 1. And then all of a sudden you have fe, -2. So we've gone all the way to the end of the range and started counting backwards. -1, you count backwards from the end of the range 1. -2, you count backwards from the end of the range 2, etc. Let's do a couple more. Let's turn a -1 into a 1, just to kind of prove that this formula of logical not plus 1 will also turn a negative into a positive if we want it to. We toggle all of the bits, and that gives us 0, and then we add 1 to it. And ta-da, we're back to +1. Finally, let's use this algorithm on 0 just to prove that it works and doesn't mess anything up. So we have all zeros. We toggle all the zeros to all ones, and then we add 0 to it again, and we add 1 to it. And what that does is if you're at 1, 1, 1, 1, 1, 1, 1, 1, and you add 1 to it, then it's going to reach the end of its range, and it's going to go back to 0. Here's a good visual representation of everything. Again, 0 is right here at the beginning of the range. The positive numbers are just normal. They just count up as normal. But negative, as soon as you go from 0 to -1, you go from the lowest number in the range to the highest number in the range. You get this 1, 1, 1, 1, etc., 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 which in hexadecimal would be represented as FFFFFF. And then -2, it goes down 1. -3 goes down another 1 until it counts down until you reach the exact middle of the range, and then you run out of room and you would flip back to positive numbers. All right, that was data types. I think one more slide here, and then we will go and submit our solution. So just a reminder, a semicolon is a comment. And then now I want to introduce these db, dd, dq. Remember, that's data byte, data double, and data quad, and those correspond to different variable sizes. And there's also dw for data word. But those three that I just mentioned are the ones we're going to use most of the time. This db we're going to need for chars, dd we're going to need for ints, and dq we're going to need for pointers. So those are going to be the most common data types that we use, that we declare as constants. This is all these D's, these D commands, these D instructions are for declaring constants. And again, this is the format you want to have. If you want to declare a string, you do the label, you do the width, you put it in quotes, you type out what you want, and then you terminate it with an ASCII 0. If you wanted to do ints, for example, you could do something similar. You'd name it, and then you need to put the correct width for the ints, which is usually going to be double, and then you just list your ints. Like, let's say we want to do an array that counts from 0 to 4. 0, 1, 2, 3, 4. And then for arrays that are a fixed width, for stuff that isn't strings, things that are just arrays, you don't even need to terminate it. You don't need to terminate it with a null character. You're going to tell the compiler when you make the array what the size is going to be, and because of that, it doesn't need a null character. It's not a dynamic array, it's a static array. All right, let's get back to our example here. We can hit this button in the corner to toggle full screen, not full screen. We already passed the tests. I think we've talked about it enough at this point. Just one more reminder. This hello here is a pointer to the data in memory. It's a pointer to the very first character right here. And putting this pointer into RAX will send the string to whatever called the function, and whatever called the function can figure out how to parse it. Alright, so attempt is going to run not just these tests down here, but it's also going to run the secret tests, just to make sure we didn't mess anything up. Sometimes you can pass the regular tests, the public tests, but when you hit attempt, you run into a secret test that doesn't work. So let's give this a try. Bam. It says outstanding. You may take time to refactor, comment your solution, submit when ready. So at that point, you can go through and make your solution look prettier, nice and compact. Maybe add some comments for some of the trickier sections. Maybe remove all the echoes and printfs and stuff like that you were using to debug it. And then hit submit one more time, and you will be taken to the solutions page. Now, the solutions page is very important. In my opinion, this is where you're going to do all of your learning. Well, except for these videos, of course. But if you're doing CodeWars on your own, this is where you would do all of your learning, examining how other people approach the same problem. And the best tip I can give you for this section is the shortest answers are usually the best. And here's why. Number one, the shortest answers, that means they used a good algorithm. That means the code that is executing is doing so efficiently. It's not using an excess number of instructions, excess number of loops, etc., etc. And the other reason is the shortest code in the solution section is probably also using the correct library functions. So when you submit a problem, if your code is gigantic compared to the other answers, that usually means you need to improve your algorithm, or you didn't know about a library function that you could have used. Like maybe you needed to get the length of a string, and you didn't know about strlen, stringlen, in C. So instead, you just made your own loop that you made your own function and your own loop that got the length of the string. In general, if there's a library function, you don't usually want to do your own function. A is just extra time, effort, and code that you don't need. And B, their implementation of it is almost always going to be faster than anything you could implement yourself. So in general, when you're looking at the comment section, you want to take a look and look for the shortest solutions, and those are usually the best. And nice thing about CodeWars is it'll actually sort the solutions. It'll put the ones that have been voted best practice or clever at the top. So let's take a look at these. This one is almost exactly the same as the one we did, which makes sense. This was a pretty simple problem. So you'll even see sometimes multiple people will submit the exact same solution. Let's take a look at this one. They just put their data section down here. Let's take a look at this one. This one, instead of putting their hello world in quotes, they decided to spell out each letter of hello world in hexadecimal. And then they did something here with a loop. Ooh, here's a solution I did back when I first started this. I also put my data section on the bottom. But yeah, pretty straightforward for this. But when you get into more complex problems, it'll actually be really interesting to look at the answers. You'll do most of your learning from looking at these answers and seeing what other people did. I'd strongly encourage you to take the time, if there's a better answer, to at least take a look at it and step through it mentally and try to understand what it's doing. Take note if they used any library functions that you didn't use. And just make sure to learn as much as possible from it. Maybe even code it out if it was a problem you spent a lot of time on, and your answer was like 5 pages long, and the best answer on here is only 1 page long. I did that recently with a problem, and I learned a lot from it. They had a much better algorithm than I did. So yeah, I think that will be about it for this video. I hope you guys enjoyed the format. I tried to keep it as code focused as possible. In future videos, I am hoping to do even less theory and more code, but I just got to get you guys up to speed on the basics. So thank you very much for watching. If you enjoyed the video, please like and subscribe, and I look forward to putting more of these out in the future. See you soon. Bye.